So today we're going to just expand and practice more the graphing of rational functions. We're not really necessarily going to learn a lot of new concepts, but we are going to sort of refine the concepts that we already know pretty well here. So let's go ahead and just take a look at a rational function, and we'll go ahead and just go through all the steps that it takes to be able to graph it, ideally without using a calculator. The goal with graphing rational functions is that we will not eventually have to use a calculator to graph any of the rational functions that you're going to see. So for instance, if I had the function r of x equals x minus 1 over x squared minus 4. All right, the first step that we're going to take to graphing rational functions is the step that we take in any other family of functions, and that is to find the x-intercepts, and we're going to go ahead and find the y-intercepts. So we want to find the zeros, and we want to find the y-intercept. Now, zeros. How do we find zeros again? Yep. The x-intercepts. How do we find the x-intercepts? Got to set
r of x equal to 0.
Exactly. We're setting r of x, which is y, right, equal to 0. And then we have an equation that we want to go ahead and solve there. Now, for any fraction, we have a fraction here, right? To be equal to 0, what has to be true? Which part of the fraction do we care about in this case? What's the only way that this fraction could equal 0?
The top part equals 0.
If the top equals 0, right? The denominator, no matter what there's nothing the denominator can be that is going to make the fraction equal to 0. Because the denominator is equal to 0, what happens?
It's not 0.
Then we're dividing by 0. What's wrong with that? It's undefined for that, and that's where our vertical asymptotes actually end up being. But when the numerator is 0, right, that's where our x-intercepts are. So for this to be true, x minus 1 has to equal 0, right? And therefore x equals 1. So for the zeros, we're always looking at the numerator of the rational function to find our x-intercepts. For the y-intercept, same as always, we're just going to do r of 0. That process isn't any different than it has been in the past. If we simplify this expression, we'll get negative 1 over negative 4, which is just 1/4. And so our y-intercept occurs at 1/4. So we're going to use those points to help us graph the function a little bit. We're not going to start graphing it quite yet, but we'll use those points in a bit to graph the function. We want to know where it crosses the y-axis, where it crosses the x-axis. Those are critical, important points. Now, the next thing we want to find is the domain of the function, which will lead to knowing about the where the vertical asymptotes lie, right? So the domain, how do we find the domain?
To find what doesn't work.
Yeah, and so to do that, we have to do what with this fraction right here?
Expand it.
Yeah, we got to go ahead and factor the denominator to figure out what values of x are going to make the denominator equal to 0, which is what is going to which are values of x that won't be part of the domain, right? So we have the function r of x, which equals x minus 1 over, and if I factor this, it's just x minus 2x plus 2, right? And so that means that x cannot equal 2 or negative 2. So our domain is going to include everything except for 2 and negative 2. So if I did it in interval notation, it'd be negative infinity to negative 2, union negative 2 to positive 2, union 2 to infinity. Right, so in other words, everything except for 2 and negative 2. So that means we have vertical asymptotes where it is undefined, right? Not only where it's undefined, but also where it's undefined and where those discontinuities are unremovable, meaning if there was like an x minus 2 or an x plus 2 in the numerator here and they canceled, then we would know that these discontinuities, instead of being vertical asymptotes, would just be point discontinuities, right? We call those removable discontinuities. But because neither of these cancel, these are both vertical asymptotes. So we have vertical asymptotes located at x equals 2 and x equals -2, right? And also, what we also know about those vertical asymptotes is because, what's the multiplicity of x minus 2 and x plus 2 here?
2. Ooh.
Well, the
Oh,
multiplicity of x,
indivisible?
it's 1 in both
Oh,
cases,
yeah,
right? Yeah,
sorry.
so when the multiplicity of the asymptote is odd, right, then you know that the asymptote is going to go up from both sides. It's going to go up from one side and then down from the other side, right? When it's even, you know it's going to go up on both sides. So these are both odd, and so we know both of these asymptotes are going to, whoops, not look like that. We know that these asymptotes are going to look something like that, right? They're not going to go both up to positive infinity. One's going to go down to negative infinity. The other is going to go down to up to positive infinity. And we can tell that just by looking at the multiplicity of these binomial factors in the denominator here. So zeros, y-intercept, domain, vertical asymptotes. We've in the process of factoring this, if we could cancel like some x plus 2s or x minus 2s, which we can't, we would then have gotten our rational function in terms of lowest terms, but it's already in lowest terms as is, asymptotes or otherwise. So going back here, we have r of x, and we'll go back to all that stuff, over x minus 2. So another thing we would like to know about this is, do we have any, what is the end behavior? So we located the vertical asymptote, so what is the end behavior? Remember, the end behavior, right, that means, do we have any horizontal or oblique asymptotes? Or otherwise, right? If they're not oblique asymptotes, that just means the end behavior is not linear. It's right, it's quadratic or cubic or whatever. So what type of end behavior do we have? Do we have horizontal asymptotes? Do we have oblique asymptotes? Do we have end behavior that's not constant or linear, right? So essentially, horizontal is just a special way of saying constant end behavior. Oblique is a special way of saying linear end behavior. And otherwise means nonlinear, right? Like a quadratic or whatever. So how do we tell, just by looking at the polynomial function we have on top and the polynomial function that we have on bottom, what type of end behavior we're going to have? What was the rule that we used from yesterday? And it all depended on the order of the polynomial in the numerator and denominator, didn't it?
Yes.
So what's happening? So the question for the end behavior is, what's the limit? What's happening to y as x goes to infinity? As x gets really, really big, what's happening? So as we go really, really far to the right on the graph of the function, what's happening to r of x, to y?
It's
small.
really small.
It's getting really small until it ends up becoming,
0.
and you knew that because why?
Is the bottom, the denominator's a
Higher order, so it increases faster as x gets really big, right? So we looked at this this function here, and we said that, well, we have a linear function on top and a quadratic function on bottom. A quadratic function is higher order than a linear function. When we have a higher order function on the bottom, it always just goes to 0. And so that means we have a horizontal asymptote, and that's going to be true no matter which direction we go to, right? If we go to infinity or negative infinity, it's going to be 0 in either case, right? And so that our horizontal asymptote, so we have a horizontal asymptote because it goes to 0, right? and that horizontal asymptote is y equals 0, right? It's just a line y is equal to 0. So we know it just goes down to 0. So we're, at this point, pretty much ready to go ahead and, last thing we want to check is symmetry. We should always algebraically check for symmetry if there is any, just so that'll help us have a better sense of what the graph should look like. So to check symmetry, what do? We're looking for either the function being even or odd, right? And how do I check for even or odd? It's the same test either way.
Plug in negative x.
R of negative x, yep. Which will give me negative x minus 1 over, I'm going to use the simplified version of this, x squared minus 4, over negative x squared minus 4. Now, when I square negative x, I just get positive x squared, right? And so that is right there. That's neither the opposite, because this expression on top here isn't the opposite of this. It's just, only one of the signs change, not both the signs. So the top on here is not the opposite. The bottom is the same. And so this expression overall is not the opposite of this expression, right? It's not the same as it, and it's not the opposite as it. So it's neither even or odd. So there's no symmetry. So sometimes our functions are just not symmetrical. All right, so at this point, we're ready to go ahead and graph the function, or draw a rough sketch of the graph, which we then can confirm with the graphing calculator afterwards. So we already determined that the only x-intercept was y is equal to 1 on the previous page. We also determined that the y-intercept was 1/4, which is like right there. Right, so we have the x-intercept and the y-intercept. And we know we have vertical asymptotes at 2 and -2. Okay, we're going to go ahead here. We have our vertical asymptotes at 2 and -2. Whoops. Fix that right there. So at -2 here is one of our vertical asymptotes. At +2 is the other one. I like it to draw dotted lines. Whoops. I like to draw dotted lines to remind myself that that's where the vertical asymptotes are. Right, and now I'm going to go ahead here and just try and, I know this has to sort of come down through here and has to cross the x-axis, so it probably goes down like that, and then goes up like that. It gets really big. And then because we know these have to be, because these, we talked a second ago about the multiplicity, since the multiplicity of these two vertical asymptotes here, the x minus 2 and the x plus 2 is 1, it's odd. That means that it has to go up to the other infinity on the other side. Right, so it has to look like that, and then it's going to go down, and it probably should look a little bit different than that. And then it's going to go down there and ultimately approach 0, and then over here it's going to do that. Right. So that's a good sense of what our function looks like, which we got just from, like I said, we haven't even touched a calculator yet, and this is an important skill to be able to look at a rational function and be able to get a rough sense of what the graph is going to look like without having to use the calculator. But now let's go ahead and just confirm that by graphing it in the graphing calculator. So we just graph that in the graphing calculator and we confirm that. It looks good, and so there we go. That's the process we're going to use for graphing a rational function right there without using our calculator. Okay. All right, so sort of giving you the outline, I'm going to give you another example here, and I'm going to have you go ahead and just graph it on your own using the same process. And that function will be r of x equals x squared minus 1 over x. So I'm just going to go through and list off all the different things that you want to do before attempting to graph the function. Number 1, find the intercepts. Or, you know what, I'm going to write that on this page, and then how about we'll just do this next example on the next page. But I'll go ahead and just write this list of things that this process that you're going to go through to graph a rational function. So, graphing a rational function. Number one, find the intercepts. For the x-intercepts, right, the zeros, we just set the numerator equal to 0, right, and solve that equation. Number two, factor the denominator and identify domain. Number three, reduce the fraction by canceling if you can, and what's left over in the denominator, then the solution to the denominator equaling 0 gives you your vertical asymptotes, right? Number four, any discontinuities that cancel are point discontinuities. Five, locate or determine end behavior, which means at that point, what type of end behavior do you have? And that means, do I have horizontal asymptotes, horizontal or oblique asymptotes, or otherwise? Right, and so that's determining the end behavior is probably the trickiest part. That involves, taking the limit, right? Taking the limit as x goes to infinity of your function r of x, whatever that happens to be, and then finding the end behavior model based on whether the limit exists or it goes off to infinity. And I can expand upon that later. Number six, lastly, is check for any type of symmetry. And as far as vertical asymptotes, the multiplicity of the asymptotes tells you whether it looks like this or it looks like that. Okay? So there's a lot of little nuances and things that you have to know. So that's the step-by-step process we'll use. For number 5, 5 is a pretty complex process, finding the end behavior, whether it's a horizontal asymptote or an oblique asymptote, or if it's quadratic or whatever else. And so for the end behavior, I think after we get done with this next example, I'll write up a step-by-step process for actually determining the end behavior. Everything else is simple enough, I think. All right, so let's go ahead and I'm just going to have you do this next example entirely on your own. Go ahead and graph the function r of x equals x squared minus 1 over x, using that step-by-step process we just identified. All right, so let's go ahead and take a shot at this now. First thing, x-intercepts and y-intercepts. So let's find some zeros. Zeros are going to happen when the numerator is equal to 0, right? That's when we're going to get our x-intercepts. That means x squared equals 1, so x could equal plus or minus 1. So we have two x-intercepts at positive 1 and negative 1. Y-intercept happens when r of 0, we have r of 0, sorry, which is going to be 0 squared minus 1 over 0. Oh, what does that mean? Yes, so it turns out it never actually intercepts the y-axis because the y-axis is itself a vertical asymptote. So y-axis is a vertical, so we sort of inadvertently found the vertical asymptote there. And there is no y-intercept as a result. So, like I said, we sort of already found the vertical asymptote. Which is just going to be the equation x equals 0. Right? And the multiplicity is 1, so we know it's going to be one of these types of, one of these types of asymptotes where they go to opposite infinities. So vertical asymptote, let's look at the end behavior. Actually, since we're on the vertical asymptote, what's the domain going to be? Domain is, I'll do this in set notation. Make sure I'm using the right set notation. Yeah. So all x such that x is not equal to 0.
It's easier.
Yeah, sometimes it is easier to use the set notation, set Miller notation, instead of interval notation. And lastly, let's determine the end behavior. Well, not lastly, because we want to do symmetry too, but end behavior. So to determine the end behavior, we have to go ahead, and we should first, and we need to go ahead and divide it out, because what do we know is going to happen? What's going to happen? First of all, with the end behavior, the first step we should always take with the end behavior is take the limit as x goes to infinity of whatever the expression happens to be. Does it go to 0? Does it go to some constant value, or does it go off to infinity? In this case, what happens? The limit is what? The numerator is a higher order polynomial.
So let's go to infinity.
Yeah, it's got to go to infinity. If the numerator increases faster than the denominator, it just shoots off to infinity. So if it goes to infinity, we could have an oblique asymptote, or it could be a quadratic asymptote, or any other type of nonlinear behavior. So we got to figure out what type of end behavior we have. The only way we can do that, if the top is higher order than the bottom, is to divide the top by the bottom using long division. Right? So we're going to do, I think I can probably fit it in here. We're going to go ahead and divide by x, the expression x squared. I'm going to put a placeholder in for x. Minus 1. And so we got to go ahead and multiply this guy by x to make it x squared. So we get x squared and nothing else, right? And then we go ahead and drop down the negative 1. And x doesn't go in the negative 1, so we end up getting that that x squared minus 1 over x is equal to the quotient plus the remainder over the divisor, right? So that means that if we go ahead and take the limit of that, right? Or it could just be x minus 1 over x, right? What do we see happens to the 1 over x part? As x gets really, really big, what happens to this quantity right here?
It's really, really small.
So this is really the only thing that matters, right? This keeps increasing, and so it's going to behave, right? It's going to behave just like the function y is equal to x. So we're going to have an oblique and that's linear, right? Meaning we have an oblique asymptote. Whoops. And that oblique asymptote is y is equal to x. Okay? So that's, the last thing, I'll do it right here. We want to talk about symmetry. And so if we go ahead and take r of negative x, we're going to get negative x squared is x squared, right? Positive x squared doesn't change anything, over negative x makes the whole thing the opposite of what it was before, right? So we end up getting that this is equal to negative r of x, and so this function is going to be odd, right? And so it should have symmetry about the origin. So if the function that we end up drawing up doesn't have symmetry about the origin, we know we made a mistake somewhere along the way. Okay, so we got to use all this information now to graph the function. The zeros, which are at 1 and -1, the vertical asymptote, so on and so forth. So let's go ahead and do that. And the oblique asymptote is important, right? So, function again, just so we have it, so the function is x squared minus 1 over x. And we can just go ahead and graph it here. All right, so first of all, the oblique asymptote is the line y is equal to x, right? So I'm going to go ahead and draw that line, dotted, of course. So there's my oblique asymptote. My vertical asymptote just is the y-axis, so there's no sense really drawing anything there. And so to figure out what the graph of this function looks like, what do we also know? We know we have y-intercepts, don't we? At 1, or sorry, x-intercepts at 1 and -1. So it has to cross the x-axis right there, and then it has to be over here, right? So probably, and it has to approach, it can't ever cross the y-axis, so it's sort of imagine, it can't quite get there. And it also has to approach this, and having to cross through here. So the only way that's possible is if it does this, right? So we can sort of just run our line through here. And then on this side, it has to pass through here, it has to approach that asymptote, and then it has to approach that asymptote. So that is what our function should look like there. Now, is that function, if we were to go ahead and rotate this around the origin, right? Imagine we rotated around the origin, would that go right directly on top of itself? It's hard to this one's hard to sort of think of. If we just think of it part by part, if I took this and rotated it a full 90 degrees, wouldn't it end up on top of this part? This part right here would go right on top of this part, and this part right here, if I rotate 90 degrees, would go right on top of that part. And so yes, we do have symmetry about the origin. We have a vertical asymptote, an oblique asymptote, 2 x-intercepts, no y-intercepts. So there. That's what the function looks like. We should get some more practice with this because rational functions are weird. And so let's look at this next one. We have r of x equals 2x squared. Whoops. Minus 5x plus 2 all over x squared minus 4. So as before, go ahead and analyze this. One thing I want you to, in this particular instance, I want you to never mind. Just go ahead and analyze that one as you have in the past. All right, so the first thing we want to do here is we want to find the intercepts, just like we did before. Whoops. All right, so we want to find our, intercepts. So the first thing we should do, especially in a situation where the top and the bottom are factorable, is to go ahead and factor the top and the bottom first. Whoops. So let's go ahead and do that. So if we factor the top, we get what?
X minus 2, or 2x minus 1.
On bottom, we get x plus 2x minus 2. Right. So what we see here is we look at the top and we say, well, shouldn't 1/2, right? Whoops, not what I wanted to do. Right, shouldn't 1/2 and 2 both be intercepts? 1/2 I agree with. Why would 2 not be an x-intercept? What's the problem with 2? 2 makes the top 0, but what does 2 also do?
Make the bottom 0.
Yeah, if anytime we have a number that's going to make the top and the bottom of the fraction equal to 0, what we want to do is we want to reduce that and get rid of that, because what's happening right here is neither an x-intercept or a vertical asymptote. Right? It's undefined at this point because it makes the denominator 0, right? And 0 divided by 0 is still undefined, even though 0 is on top as well. And so it's undefined here, but because it cancels out, it's not a vertical asymptote. So it's anytime we have a factor that occurs on top and on bottom, what we want to do is just cancel it, right? But remember that it's undefined right there, and the reason for that is we just have what we call a point discontinuity. So it's defined just at this particular point, but it doesn't create an asymptote, and it's not an x-intercept. So if we go ahead and cancel those, the function that we want to look at to actually figure out the x-intercepts and the asymptotes is the function 2x minus 1 over x plus 2. But we have to remember still that x cannot equal 2. So we have a point discontinuity there, right? Point discontinuity at that point. All right, so our x-intercept or zeros are at 1/2. And we have a y-intercept. R of 0 is going to give us negative 1/2, right? Because looking at this version here, if I plug in 0, 0, 0, those all go away, and we're left with 2 over 4, which is the same. Oops, which is just the same as negative 1/2. Vertical asymptotes. We have at x equals negative 2, right? And multiplicity ones, this one's just going to look like this, right? Domain. It's just going to be all x such that x is not equal to negative 2 or positive 2. So this one still, once again, it's not a vertical asymptote, but it does take away from the domain. Okay, now let's talk about end behavior. Right? What is the limit as x goes to infinity of our function r of x? Now, if we look at this function right here, anytime we're trying to take the limit and the top and the bottom, right, have the same, they're both second order, they're both quadratics, right? So they both increase at roughly the same rate. What do I need to do then at that point to determine what the limit is as x goes to infinity? They both increase at the same rate, meaning what's going to happen? They're going to go to a constant other than 0. So they're not going to go to 0, they're not going to go to infinity, they're going to go to some constant in between 0 and infinity. And to figure that out, what do?
Long division?
Nope, we don't have to do long division for this one. For these ones, we can just go ahead and get rid of all the lower order terms, right? Get rid of the negative 5x, the 2, and the negative 4, and that just leaves us with, if we eliminate all of our lower order terms, it just leaves us with 2x squared over x squared, which reduces to 2 and gives us a limit of 2, right? So that means I have a horizontal asymptote that goes to a constant value, either 0 or anything else. That's a horizontal asymptote of y equals 2. And lastly, let's take a look at symmetry. R of negative x is going to give me the 2x squared is not going to change, right? But the negative 5x is going to become plus 5x. The positive 2 is not going to change. And on the bottom, the x squared is not going to change. So that's neither even or odd. The only one sign change is not enough to make the entire top or entire bottom negative, right? And so this is not the opposite of this. This is the same as this. So these together are not opposites. And so we have no symmetry. Not odd or even. Oops. No. Go. So there we go. So we pretty much have all the information we now need to go ahead and graph this function. So let's go ahead and do that in the next page here. We have our function r of x equals, I'm going to write it out in the factored form, 2x minus 1 times x minus 2 over x plus 2 times x minus 2. So if we go ahead graph this. Right, we know we have a horizontal asymptote at x equals -2. Sorry, vertical asymptote at x equals -2. So let's go ahead and draw a vertical line for that. We know we have an x-intercept at 1/2. So let's say 1, 2, right? So 1/2 is like right there. So that's our x-intercept. And we know we have a horizontal asymptote at y is equal to 2. So 1, 2. Let's draw a dotted. Horizontal line for that. All right, and so we know that if it crosses here, right, and it has to approach here, it probably does something like this, right? It has to go down and approach that. It has to go through this point, and it has to approach that asymptote and approach that asymptote without ever quite crossing it. So it probably looks like this. Oops. And then that would mean that what type of this is that means it has to come down from the other infinity there, right? It has to go off in this direction, and then that would mean because that asymptote it's going to have to go off over there. Now the last thing we should take into account is the fact that at 2 we have a discontinuity, right? There's a point discontinuity there, and so to indicate that, we just are going to make a little open dot there to indicate that it's not defined at 2. It's defined everywhere else except for 2. Right? So there we go. We have our vertical asymptote, horizontal asymptote, point discontinuity, all that nicely graphed right there. And lastly, we should always, of course, go and confirm that by graphing it in our graphing calculator just to make sure. And the graphing calculator confirms that we are correct in our assumptions about this function. Okay. So, the question becomes, well, can I do this all in reverse? All right, can I write the formula for a function if I'm given the graph of the function? Can I take it backwards? So let's look at an example. So, as in this example right here, if we're given the graph of the function, can we construct the formula for the function from the graph? All right, so what I would do here is I would start by looking at this, and let's go ahead and identify where are our asymptotes. Well, let's look at, our intercepts first. Find our intercepts, so our x-intercepts. Where do they occur? They occur at x equals -2 and 5, right? So those are our two x-intercepts. Y-intercept occurs at -2. Vertical asymptotes at where? -5 and 2. And horizontal asymptotes at y is equal to 2. So if we're going to go ahead and start constructing this, I'm just going to call this function r of x. I'm going to slowly start putting it together here. I know that if -2 and 5 have to both be x-intercepts, then x minus 5 and x plus 2 have to be factors, the numerator, right? So let's make those factors the numerator. X plus 2 and x minus 5. Now, with the x-intercept at x minus, or at -2 here, what's happening? It's just touching it and then going back down. So what do we know about x-intercepts? Going back to what we knew about polynomial functions, where it just grazes it. What has to be true about the multiplicity of that particular?
It has to be even.
It's got to be even. So let's make that x plus 2 squared. Now, for the things that need to be in the denominator, well, if we have vertical asymptotes at -5 and 2, that means x plus 5 needs to be a factor of the bottom, and x minus 2 needs to be a factor of the bottom. Now, looking at this asymptote right here, we see that one side goes up to positive infinity, the other side goes down to negative infinity. So this asymptote has to have a multiplicity of what?
1.
1, so we'll just leave the x plus 5 as is. But for the x minus 2, these both go down negative infinity. So what has to be true about the multiplicity of this asymptote? It's going to be even, so we'll make it x minus 2 squared. Now lastly, the order on top and the order on bottom would be what? They're both, if I multiply these out, I'd have a what on top and a what on bottom.
Quadratic.
I have 1, 2, 3 binomial factors.
Oh, 3, yeah.
Yes, it'd be a cubic on top and the same thing on bottom. So we have same order on top as on bottom, and it would just be, the leading term would just be x cubed, right? X cubed and x cubed, and so that would go to, if I took the limit as x goes to infinity, it would go to 1, wouldn't it? It would just be x cubed over x cubed. How can I make that so it's 2 instead? So instead of going to having 1 as a horizontal asymptote, how can I make it have 2 be a horizontal asymptote?
Multiply the numerator by 2.
Yep, take the whole numerator, multiply it by 2, and now I have that horizontal asymptote of 2, right? So that's all we got to do. Let's go ahead and check that by plugging into our calculator and confirm that that actually looks like the function we think it does. So yeah, that's all we got to do. It's in a lot of ways this is easier and quicker than actually graphing the function from the formula, to actually build the formula from the function. Last thing I want to make a note of really quickly, we notice there is a relative maximum right here. So it is possible in some cases, not ever, in a lot of cases there aren't any relative maxes or mins in rational functions, but this one has a relative max right there. So there's a relative max at the point -2, 0. So just know that rational functions can have relative max and mins, and you might have to use that fact to find the maximum or minimum of the function over a certain domain. Okay? All right, so that's it for today. Let's go ahead and take a picture of the homework here. So that's the homework assignment for tonight. It comes from the handout that I emailed out to everybody. I also emailed out the Chapter 2 test that I promised, and the solutions I will email out. I will write out solutions to the Chapter 2 test. I will email solutions to you guys tomorrow. So whenever you get a chance, I would highly recommend that you go ahead and take the Chapter 2 test. I would sit down with it without your notes or the internet or anything, and just see what you can do with a graphing calculator and just your mind to get through it from start to finish, and then look at my solutions after the fact, not before. Don't look at the solutions beforehand, and check to see what you got right and what you got wrong and what you need to work on, so that you have a really good, honest assessment of how you're doing. Starting tomorrow, we're going to be holding classes at 9:30 instead of 4 p.m. Because my mornings are cleared up and it's more convenient to do it in the morning, and everyone who's coming in the afternoon would just assume have it in the morning as well. So classes starting tomorrow are going to be at 9:30 a.m. Anyone who hasn't been able to make it because they haven't been able to do the afternoon in the past, feel free to come by and stop in for class tomorrow at 9:30. All right, have a great day, everyone.